Hello, everyone. Whether you're here with us at the Mesa Lab or joining us virtually, thank you for sharing your time with us today for this NSF NCAR Explorer Series lecture, There's Something on the Wing, Something Green, with Dr. Scott Landolt. I am Evan Portier, and I am an education designer here at the U.S. National Science Foundation, National Center for Atmospheric Research, otherwise known as NSF NCAR. NSF NCAR is a world-leading organization dedicating to understanding Earth system science, including our atmosphere, weather, climate, the sun, and the importance of all these systems to our society. I'm glad that you're all joining us today to learn more about the science behind de-icing fluids that Scott will present on. For this event, you'll be able to ask Scott questions following the lecture. If you're in person, you can raise your hand and Perrin will give you a microphone and you will have time to ask your question. If you're joining us virtually, you can ask your question using the Slido platform. If you scroll down this webpage, you'll see the Slido window. Well, you'll see the Slido window just below where you're seeing the live stream video of this event. If you haven't already, go ahead and click on the green Join Event button, and then you can ask questions on the Q&A tab. Scott also has a few questions for us. So for both our in-person and virtual audience, you can respond on Slido. For those in person, you can use your phone or laptop to navigate to slido.com and enter the code #ExplorerSeries, or scan the QR code right there. And definitely be sure to join Slido to add your thoughts to our word cloud question. Think of a time you or someone you know traveled by air during winter weather conditions. What's one word you would use to describe that experience? Because we're going to get to that soon. This event is being recorded and will be available on the NSF NCAR Explorers website. And so, with all that, I'm going to introduce Dr. Scott Landolt. Scott Landolt is a scientist at NSF NCAR and has worked in the Research Application Laboratory for over 25 years. 25 years. One of his primary research areas focuses on improving snowfall measurements and observations. He was an active participant in the World Meteorological Organization Solid Precipitation Intercomparison Experiment, also known as SPICE, to establish a world standard for snowfall measurement. More recently, Scott has been actively working with the Federal Aviation Administration, or the FAA, on developing methods to utilize snowfall measurements with aircraft de-icing practices. In addition to his research, Scott oversees the Advanced Study Program. Outside of NSF NCAR, Scott is a professor at the Metropolitan State University of Denver in the meteorology program. Now, before I turn it over to Scott, let's go ahead and check our thoughts on the word cloud. Joey and Christopher, would you mind sharing that Slido for us? With that note, I'm going to let Scott take it away.
Perfect. Fantastic. Thank you, Evan, and thank you, everyone, for joining us tonight. Delayed pretty much sums it up. So one of the things I'll be talking about throughout this lecture tonight is why you are delayed and what results in a lot of those delays. But one thing I will say is oftentimes it's better to be delayed than canceled. So keep that in mind as we go through this talk as well. Perfect. All right. Then I think we can go ahead and switch back over to the presentation. There's something on the wing, something green, as William Shatner would say. So what are we going to be talking about tonight? I'm going to start the lecture off giving you kind of an overview of aircraft de-icing, what's involved with that, what goes into it. So we'll talk about why we need to de-ice. We'll talk about the types of fluids that are used in the de-icing process. And generally how the process itself actually works. And then once we get through that, the next part of the talk will focus on what we at NCAR have been contributing to that process. So we're going to talk about the science behind the fluids, how they work, the discoveries that we've made, as well as the ongoing research that we have with the FAA to continue to improve aircraft safety when you're flying in winter weather conditions. So I want to start off with the idea of what's referred to as a clean wing concept. The clean wing concept is really that when you are in an aircraft and you're getting ready to take off or you're in flight, you want to make sure that your wing is free of any type of contamination. The wing is the surface that gives you lift. It allows you to actually fly. So when you have a clean wing, you have nice flow over the top of the aircraft. Now what happens when you're sitting on the ground or you're flying through precipitation in the air and that precipitation starts to build up on the wing? That's where we get what we call our frosty wing, where we start getting things adhering to the top of the wing. This is really our critical surface, and you note from the figure up there that the airflow stops becoming nice and smooth over the top of the wing, and instead you start getting these little eddies that develop. It's problematic because that's stealing lift from the aircraft, so it becomes harder to fly. Additionally, because you're getting contamination on the wings, you are also adding weight to the aircraft, which means now you're also going to start consuming more fuel, trying to keep the aircraft airborne at the speed that you're flying. So how much contamination on the wing is potentially too much that would cause a problem? Literally as little as 1/4 of an inch of buildup on the wing is enough to affect lift on your aircraft. That'll, as I said, increase drag, it increases weight, it decreases your lift, and if you're trying to take off from the ground, it can definitely cause you problems. So let's talk about some of the incidents that have occurred in the past that highlighted the dangers associated with snow buildup on the aircraft on the ground. The first one I want to talk about is Air Ontario Flight 1363. This accident happened back in 1989. This was an aircraft that was flying from Thunder Bay to Winnipeg, and it stopped in Dryden to do a quick fuel up. The problem was when they landed, the auxiliary power unit on the aircraft stopped working. And that meant if they turned the engines off, they would not be able to get the engines restarted. That aircraft or that airport is actually also a very small airport, so they didn't have power that they could hook up to the aircraft to allow the aircraft to start the engines again. So while they're stopped there, they're fueling up. It was lightly snowing at the time. The pilot said, well, I can't turn the engines off, and regulations state that you cannot de-ice an aircraft while the engines are running. So we simply won't de-ice the aircraft. So before takeoff, it was noted that roughly 1/4 to 1/2 an inch of snow had built up on the wing surface. And as they were getting ready to take off, they became airborne briefly, but because of that added friction on the surface of the tops of the wings, they couldn't gain altitude because they didn't have enough lift. They ended up clipping the tops of the trees at the end of the runway, and the aircraft crashed, killing 21 of the 65 people on board. So there was a lot of recommendations that came out of this, obviously, one of them being you must de-ice the aircraft if you suspect that there is any contamination on the wing. Fast forward another 3 years, US Air Flight 405 crashed coming out of LaGuardia Airport out of New York on March 22nd, 1992. This aircraft had actually come in from Florida. It was flying in, it was actually late getting into the airport. So when they got on the ground, there was already a rush to try to get caught back up. So they quickly got all the passengers off the aircraft. They got the new passengers on. The pilots called for de-icing of the aircraft. So the trucks pulled up, they de-iced the aircraft, and one of the trucks stalled behind the aircraft. It took 20 minutes for them to get the stalled truck moved from behind the aircraft so that they could get the aircraft on its way. At that point, the pilots called for another de-icing of the aircraft, as they should. So 2 more trucks came out, they de-iced the aircraft. The aircraft went to get in queue to take off, and they were further delayed because it was snowing. So everything had slowed down, and by the time they got to the front of the line, they had been on the ground almost 40 minutes from the time that they had de-iced. Throughout that time, the pilots kept looking back. They were looking out of the cockpit window back at the wings. They couldn't see any buildup of ice on the aircraft. One of the aircraft behind them also reported that they didn't notice any snow or anything building up on the wings of the aircraft. So the pilots started the roll down the runway, went to take off, and as soon as they became airborne, there were problems. The aircraft was struggling to maintain altitude, to stay in the air. The pilots quickly realized they were not going to become airborne, but they were running out of runway. So in the process of trying to get the plane back down, the left wing clipped the ground and dragged along the runway for about 100 feet. Ended up crashing over the seawall and into Flushing Bay. So in this accident, 27 of 51 people on the aircraft were killed. The NTSB review of that revealed that what had happened was during their long time of sitting on the ground, snow had dissolved into the fluid and the fluid had frozen over the top of the wing. So it looked like the wings were just wet when in fact there was a relatively thick layer of ice on the wings that prevented them. So added weight, increased drag, no lift, we had another accident. So a lot came out of these two particular accidents in terms of our knowledge of what we need to do to make sure that these accidents don't continue into the future. But what did we do before we had de-icing fluids? A quick history. Back before 1950, when we introduced some of the first de-icing fluids, they would send crews out with scrapers and brooms, literally to scrape snow and ice off of the aircraft wing surfaces. Now you can imagine nowadays, a 787, you probably don't want to have a crew of people with scrapers and brooms trying to brush snow off of the wing of the aircraft. So they quickly realized this was not going to work. Also, this only works after the snow is done. This doesn't address problems while it's still snowing. So we came up with the more modern idea of applying these de-icing fluids to remove contamination from the aircraft. And that is what we continue to use this day. So I'm going to give you a little bit more details on the de-icing fluids themselves. So when an aircraft goes out for de-icing, the de-icing portion, the fluids that are used, we refer to as type 1 fluids. These are non-thickened fluids, and that's important in what I'm going to be telling you on the next fluids that we talk about. And these fluids are typically water and a propylene glycol mixture. For anybody who's familiar, propylene glycol is the same chemical that's used in antifreeze in your cars. So it's literally the same components that we're using to de-ice the aircraft. The de-icing fluids are applied hot at high pressure. So the idea is not only do we want to melt any of the precipitation and contamination on the aircraft, we want to blast it off the aircraft as well. We want to make sure that there is nothing left sticking to the surface of the aircraft. These types of fluids are typically orange or pink in color when they're applied. So anybody who's been through the de-icing process, when you're sitting there, especially if you have a window seat and you look out, you notice the first thing is probably you're going to see this orange fluid kind of dripping down over your windows as you're going through the de-icing process. However, de-icing is just one part of that process. So de-icing will remove the contamination, but if you're in a situation where you still have snow and ice that are building up on the aircraft, and the aircraft isn't ready to take off, you need to do something to prevent snow and ice from building up. So in that case, we have anti-icing fluids that are applied to the aircraft. Anti-icing fluids are referred to as type 2, 3, and 4 fluids. These are thickened fluids, and I'm going to talk a little bit more about that coming up. They're applied at ambient air temperature, so we do not heat these ones. We want them to reside at ambient temperature, basically so that the fluid will stick to the aircraft a little bit more. The purpose of this is really to absorb any of the falling precipitation, so rain, freezing rain, snow, freezing drizzle. Anything that's coming out of the sky is going to land in this fluid, and this fluid is going to absorb that precipitation. These fluids are typically yellow or green in color, and they're either propylene glycol or ethylene glycol-based fluids. The type 2 were the initial anti-icing fluids that they came up with. After they realized, yeah, we can do de-icing, but if an aircraft is going to take off in these continued snowfall conditions, we need to provide protection. Type 2 was what they came out with. That color is mostly straw in color. The type 3s are designed specifically for commuter type aircraft. These are aircraft that are going to take off at lower speeds. And I'll talk a little bit coming up about why that's important. The Type 4s were introduced in the early to mid 90s. They're emerald green in coloring. And all of these Type 2, Type 3, and Type 4 fluids can provide protection up to 2 hours, depending on the conditions that the aircraft is experiencing. The nice thing about the Type 4 fluids, if you run out of Type 1 fluid, you can simply dilute a Type 4 and you can heat it up and use it as a de-icing fluid also. Now, I have some examples. Here is a Type 1 de-icing fluid. So I mentioned that this is a non-thickened fluid. So you notice it's very watery in appearance. So when you apply it to the aircraft, it's heated, it's gonna remove the contamination, but it's also gonna run off of the aircraft very quickly. So it's not gonna provide you much protection. Our other types of fluids, we have a Type 2 fluid. So that's our fluid that's kind of straw-like in color, a little bit yellow. Here's our Type 3 fluid, which is more for the commuter type aircraft. And then we have our Type 4 fluids as well. Now the difference, you notice with the Type 4 fluid, it's much more thick. So these fluids are really designed to adhere to the aircraft surface and provide protection so that as it's precipitating, it's not running off really quickly, it's sitting there, it's absorbing that precipitation. Incidentally, we also call this our Slimer fluid because of the green coloring. Why might the fluids be different colors? And again, this is for all of you in person as well as those of you online. So I will turn it over to our AV people and let them bring up the Slido questions so you can answer that. So here's our answers. Different chemicals or markers. So I don't drink them, so I know which is which. Fair, I will say you do not want to drink these fluids. Indicates the pilot's mood, also fair. To distinguish them from different fluids, yes, and we're gonna come back and touch on that. To handle different types of ice, also a good one. Different compounds for effectiveness in different temperatures or to tell the difference between different types. So congratulations, you have all hit on the correct answers. The coloring is really twofold. One, it's so the de-icing people, when they're applying these fluids, they can tell which sections of the aircraft they have done versus the sections that they haven't. The initial fluids were not colored. So when you applied it, especially if it's precipitating, it's really hard to tell where the fluids were on the aircraft. So then we colored them different colors so that you can tell Type 1, the very distinct pink-orange color, versus the Type 2 or 3, 4 fluids when they're applied to the aircraft. So, well done, congratulations. You're all on my same wavelength. Fluid visibility, perfect. All right, let's switch back over. Now, I wanna talk a little bit more about these thickened fluids. Now, I said at the beginning of the lecture that there's this clean wing concept. When you go to take off, you don't want anything on the wing. However, this Type 4 fluid, when you apply it, sticks to the wing. That's bad, right? The Type 4 fluids actually had a little bit of engineering that went into them. These fluids have a special polymer that chemists have designed that actually makes the fluid thick. So the idea is you put these polymers in the fluid, you put it on the aircraft wing, and it's thick, and it's viscous, and it's sticky. But we refer to these fluids as a pseudoplastic fluid, meaning that when there is a shearing force applied to these fluids, those polymers break down, and this Type 4 fluid will actually turn to the same consistency as a Type 1 fluid. I have up here a demonstration. So one of the testing mechanisms that we use is taking an artificial wing surface, which is what you see in the picture here, and this is actually a video. I'll start this video running in a second. This is in a wind tunnel. So we have Type 4 fluid, you notice the emerald green coloring, and there has been precipitation that has been applied to this. So they've applied ice pellets in the wind tunnel to this fluid. And I'm gonna start this video running here. Come on, maybe. There we go. You notice the flashing. So the flashing is a series of cameras that are set up to take pictures at certain times. And what's gonna happen is they're gonna turn the wind tunnel on. So we have a fluid that has absorbed a bunch of precipitation. It's clearly stuck to the surface, but now we're gonna simulate an aircraft accelerating up to 100 knots. So as the wind gets stronger and stronger, you notice that the fluid becomes thinner and thinner and actually runs off of the wing. So you would imagine at this point, the aircraft is going down the taxiway. It's reached the speed at which it's getting ready to take off. The fluid has now completely run off of the wing along with all of the contamination. And now the wing tilts up to simulate the aircraft actually taking off from the ground. So now we have a fluid that provides protection to the aircraft. It's going to stick to the aircraft when you need it to stick to the aircraft, and it's gonna run off of the aircraft when you don't want it sticking to the aircraft anymore. So a lot of engineering has gone into these particular fluids. As far as the anti-icing process itself, how long those fluids are going to last is really determined by the type of precipitation that's falling. Is it snow? Is it ice pellets? Is it a combination of mixed precipitation? The rate that the precipitation is falling, and the airport layout also has an impact on this. So there are two different ways in which aircraft can be de-iced at an airport. There's gate de-icing. This used to occur at Chicago O'Hare all the time. The aircraft would pull up to the gate, people would get off, the new people would get on, they would load all of the luggage, and then before they pushed back from the gate, the de-icing trucks would come up and de-ice the aircraft. The problem with gate de-icing is as soon as you apply the fluids, you have a certain amount of time you have to get airborne before you have to apply those fluids again. When you do it at the gate, then you've got to wait for somebody to push the aircraft back, and then you've got to start taxiing, and then you've got to get in line. So you're cutting into the time that it takes that these fluids are gonna last. Also, you're creating some hazardous conditions on the ground because de-icing fluid is extremely slippery. So there are a lot of slip and fall accidents that occur with the ground crews who are loading and unloading baggage on the planes as well. The central de-icing facilities, on the other hand, are a big area at the airport, and DIA actually was one of the airports that kind of spearheaded this when they built this back in the 90s. It's a big pad that's located right next to the runway. So the idea is the aircraft will go out to this pad, all of the de-icing trucks are there, you pull up, the trucks come up, they very quickly de-ice you. If they need to, they will anti-ice you. You're given clearance at that point that you're good to go. Usually you're first or second in line, so you pretty much go, you get on the runway and you take off and you're out of there in 10 to 15 minutes after the de-icing process. So the central de-icing facilities are really the way that airports are trying to move to cut down on a lot of the times that are needed for aircraft taxiing while you've got these fluids on the wings. So I get a lot of questions once I've talked about these different fluids. The most common one is, how long does the fluid last? Meaning, how long does it provide protection to the aircraft? There's a lot of factors that go into that. The outdoor temperature, for example, with the type 4 fluids. So I talked to you about how we have these polymers that are in this fluid. These fluids are also known as non-Newtonian fluids because not only do they become less viscous with the shearing force, but also as the temperature gets colder, the fluid gets thinner instead of thicker. And the reason is that the polymers that they use in here in colder temperatures actually start shrinking down. And so that naturally causes a thinning of the fluid itself. So the thinner the fluid, the more it's gonna run off of the wing, the shorter the amount of time it's gonna provide protection to the aircraft. Precipitation type and precipitation rate, I've mentioned as well as factors in that, as well as the fluid type, meaning is it type 2, type 3, or type 4, but also the manufacturer of the fluid, and the dilution of that fluid. A lot of these fluids can be applied at 100% concentration, or you can apply water to them and thin them down a little bit. That will allow you to use less fluid, especially if you're in conditions of really light precipitation and you know the aircraft is going to get off the ground relatively quickly. So it's a bit of a cost-saving measure for the airlines in that regard. Another question I get is, how do pilots know when the fluid may no longer be providing protection? Which is also an excellent question. Pilots use a thing called holdover timetables. Holdover meaning the amount of time you have from when the fluid was first applied to the aircraft until that fluid is likely no longer providing precipitation or protection from precipitation to your aircraft. These holdover times are specific to the fluid type and the manufacturer, meaning every time a manufacturer comes out with a new fluid, they have to go through an entire certification process with the FAA and Transport Canada before that fluid can be used on an aircraft. And one of the things that comes out of that is these holdover tables. Now, this is exactly one of the tables that a pilot would use. I know it's a little bit busy, but I put it up here just so you can see what a pilot has to deal with when they're going through the de-icing process and they have to figure out how long this fluid is gonna last for them. So I'm gonna walk you through how this table is used, and then I'm gonna give you an example. So the first thing that they need to know is outside air temperature. So they're given information in the cockpit as to what the current weather observations are at their airport. They'll look at this chart and say, okay, the first thing I need to know is ambient outdoor air temperature. They need to know the fluid concentration, the fluid water by percent volume. That will be given to them by the ground crew that's telling them what type of fluid is being applied to the aircraft. And then they have to know what the precipitation type is. So this table will give them times for freezing fog or ice crystals, snow, freezing drizzle, light rain, and rain on a cold-soaked wing. Cold-soaked wing being an aircraft that has just landed. It was up flying at altitude where it's minus 60. It comes in to an airport, and maybe the airport temperature is slightly above freezing and it's raining, but your wing temperature is below freezing, which means rain hitting the wing is gonna freeze on the wing. So they have a category for that as well. Anything else listed up here, they don't have any guidance for, which falls over in the red area there. So if a pilot is told that it's minus 5 degrees Celsius out there, so that would fall somewhere in this range right here. The fluid concentration is 100%, and the intensity is light snow. They would know that they have 55 minutes to an hour and 50 minutes of protection for the fluid that has been applied to their aircraft. Now, the next question you might ask then is, why is there a range of times associated with these fluids? And how do pilots know where in that range does their conditions fall? I'm gonna pick on snow as an example. So very light snow has a precipitation rate of 1/100th of an inch to a 15,000th of an inch per hour. So this is very light snow that would be coming down. Light snow is a 15,000ths of an inch per hour to 4/100ths of an inch per hour, and moderate snow is 4/100ths of an inch per hour to 1/10th of an inch per hour. Now, these measurements are not in terms of depth. They're in terms of liquid equivalent. So if you took the snow and you melted it down to figure out how much snow is in that water, these are the rates that we're talking about for this. So a pilot will get an observation of minus 5 degrees Celsius and light snow, and knowing all of that information, then they would be able to go over there and see what their range of times is. For airports that have custom systems that can accurately measure these precipitation types, those systems will actually tell the pilots what that specific time is within that range. But at airports that don't have that specialized systems and pilots are simply relying on these charts, for safety purposes, they will simply go by the shortest time available shown on these charts. Also, this particular chart, you notice at the top it says generic holdover times. As I mentioned, each fluid has its own specific holdover table. There are instances where a pilot may not know what the manufacturer is of the fluid that's being applied to their aircraft. In that case, they would go to the generic holdover table, which has all of the most conservative times, meaning all of the shortest times for every single category compiled into it. And so that way, no matter which fluid you're using, you know you will always be within your, quote, holdover time for that fluid. Then the next question is, how are these times determined? The current standard right now is that there is an organization, APS Aviation. They're based out of Canada, and they do the majority of the testing of these fluids to come up with these holdover tables. So they have this setup that you see here. It's a series of plates, and those plates are angled at 10 degrees. That 10 degree is done intentionally to simulate the angle of an aircraft wing, the top of the aircraft wing. So you apply the fluid to the top of the aircraft wing. We want to make sure that as the fluid is slowly moving down the wing due to gravity, we're simulating that same thing with these tests. So we have a bunch of different plates set up, and we go out and we pour the fluids on the plates. We also have what are called rate pans that aren't shown here, but they're pans similar in size to these plates that they put out there. They also coat with fluid. They'll leave them sit out there for 10 minutes. It will snow on those pans. They'll weigh them before they take them out, and then they bring them inside and weigh them again. Subtract the difference, and they know how much snow, liquid equivalent, fell into that pan. So they do that continually throughout the test until these fluids fail. So failure of these fluids is determined when you're visually looking at these plates and you can see that snow has built up over at least a third of the plate. And you can see some of the different plates here. This second one in here obviously is way past its failure time because it's mostly covered in snow. This first one, you can see a little bit of snow building up at the top, but it still has some time yet before it's going to be considered failed. Now, there are problems with doing this. Conditions outdoors are rarely ever constant. So you set these plates up, you let it precipitate, a snow band may move through. So maybe initially you've got really heavy snow, and then throughout the course of the testing, it may taper off to lighter snow. Also, the temperature throughout the time that you're doing the testing may change as well. Maybe it's warming up, maybe it's cooling down. So that then becomes a problem of how do you start addressing those variables when we know that they impact how long these fluids are going to last. There's also the problem too with winds. Winds are also rarely calm, and winds can further impact some of the fluids, and I'm going to talk about how that is in some of the data that we've analyzed on the NCAR side to show that wind actually does play sometimes a very significant role in how these fluids react. So I'm going to start off with this chart. Using the assembly that I just showed you outdoors, they would go out, they would pour these fluids on, and for a given temperature range, they're aiming to have snowfall rates at all different intensities. So this plot shows you a plot of failure time, meaning the time that the fluid actually failed, versus the liquid water equivalent snowfall rate. We can see it's not a linear relationship, it's a power relationship, but the line that you see going through the points on there is the best fit line. So for light intensity snowfall, that's the area in gray that you see on here. To come up with the times in that holdover table, you would simply look at this line and say, here's the short end of the time for light snowfall rates, and here's the longer time. The longer time is up here, the shorter time is down here. So going out and doing this testing and getting a bunch of these different data points and then fitting one of these lines and looking at the ranges of light is how we come up with those ranges of time. This chart looks good. The dots are all very close to the line, which is what you want to see until you look really closely at this plot. Notice the 2 points that I have arrows pointing to on this plot. These points have roughly the same liquid water equivalent snowfall rate. However, their failure times are very different. The one on the bottom had a failure time of about 35 minutes, but the one on the top had a failure time of 90 minutes. There's almost an hour difference in these 2 particular tests, and yet the average liquid water equivalent snowfall rate was the same for the 2 of them. This is where the FAA and Transport Canada and everybody is saying, why is this? Why do we see these conditions? And a lot of it goes back to the outdoor testing where you have variations in the snowfall rate throughout the test. Maybe the average rate was 0.03 inches per hour, but maybe it was really heavy at the beginning for one of the tests, and maybe it was really heavy toward the end for one of the tests. And so because of that, you end up with very different failure times of your fluids. So that means we need a controlled environment to do this testing in. So this was recognized back in the 1990s, where the FAA, Transport Canada, APS Aviation said, outdoor testing is okay, but we really need to have a laboratory-controlled environment where we can do this testing. That means we need to find a way to bring the snow indoors. So we have to develop a method where we can have it snow indoors, and we can control these variables that we think are having impacts on the fluid failure time. So we need to be able to control the temperature, and we need to be able to control the snowfall rate. So that brings the question, okay, how do we bring this indoors? Which brings me to my next Slido question for audience participation. How would you make it snow in a laboratory? And I'm very impressed with all of your answers so far, so let's see if you can nail this one also. Snow machine, build a snow machine. Clearly there are some of my colleagues who are calling in online who are cheating and answering this question. Pray and ask God to make it happen. Probably not gonna work so well, but we have not tried that. Shave off pieces from a block of ice and let them fall. Again, that would be one of my cheating colleagues online. Use the same stuff as they use at the ski resorts. What a novel idea. Let's lead with that. Let's go back over to our presentation. Okay, so if we're gonna build an artificial snow generation system, the requirements that we have are that the size of the snowflakes that we're going to be creating have to be realistic. They have to be the same size as what we're seeing outdoors. The density must match real snowfall. The spatial distribution, meaning the pattern of the snow falling over that test surface that I showed you, has to be even. And the fall speeds of the particles must be realistic. You don't want snow falling at 10 meters per second and plopping into the fluid because that's gonna cause problems. So the first thought we came up with was, let's look and see what the ski resorts do. So we said, okay, let's go check that out. Now, ski resorts use the idea of taking water and spraying it into a very cold environment to create their snow. So we went out, we gathered some of the snow industry snow that they create, and we looked at it under a microscope, and this is what it looks like. It does not look like snowflakes. In fact, they are very small frozen water droplets, many of which have actually frozen to each other. So in this case, it's actually more like really tiny ice particles that the ski areas are generating. That obviously means the density is not going to be right. The snowfall rate isn't going to be right. So this was not really a good, viable option for us. But we said, if we can't use ice in this manner, we could always think of shaving ice, like a giant shaved ice machine. So we ran with that idea, and we developed the NSF NCAR FAA shaved ice snow machine. The idea behind this is that we create cylinders of ice that are loaded into a linear translating system that feeds them into a specially designed Forstner bit that shaves the ice off that creates snow-like particles. Great in concept, actually works fairly well. I will say that this particular process has been something that we have been working on for decades now, because while it may seem simple in concept, there are a lot of little nuances in being able to create this. And I'm going to talk about some of those. So let's start with the ice creation process. How do we actually create the ice cylinders themselves? Initially we thought, perfect, we're going to get a metal cylinder, we're gonna put some water in it, and we're gonna stick it in a cold room, we're gonna let it freeze, and then we're gonna bring it out into the open, into the warm room, and that cylinder is gonna warm up, and we're gonna be able to pull the ice cores out, and they're gonna be perfect. The problem was, ice likes to freeze from the top down. So when we put it in there, ice would freeze at the top, which would then increase pressure at the bottom as it was freezing down, and we would break the bottoms off of our molds. So we needed to devise a method to get it to freeze from the bottom up. So here's an example of our ice molds that we use. So we take insulation and we put really heavy insulation at the top, and then we taper it down to no insulation at the bottom. And this essentially solved our problem. So now it will actually start freezing closer to the bottom first, and then that water pressure gets pushed upwards so that now you get freezing from the bottom up. To give you an idea of how big they are, this is an example of one of the ice cores that we feed into the machine itself. And this is one of our cores. So you can see nice formation of ice. Once you do that tapering, you do get lots of air and stuff that tends to get trapped in it, but for the most part, you actually have a really nice ice core that then you can take out and you can load into the machine itself. Okay, so we solved the ice core problem. We were able to get these nice cylinders of ice that we could then load into the machine. So the ice cylinder is mounted to a linear translating system. So those of you familiar with a 3D printer, same type of idea. We have this device here, which is our connector. So we load the ice into that. It's attached to a lead screw and a stepper motor back here. So the stepper motor turns, which then moves the ice along and feeds into a Forstner-style bit at the other end of the machine. This is one of our original designs that we had come up with from the machine. At first, we simply just had the translator and the Forstner bit, and we would turn the machine on, and of course, the ice shavings would go everywhere. All over the top, all over the sides. So you can imagine when you're trying to do testing on some of these plates, when you get it down to the bottom of the machine, eventually you get big clumps that fall off the top of the machine and fall down onto the plate at the bottom. This was a problem for many, many years. We finally came up with this idea where we have this half-moon crescent shape that is very close to the drill bit itself, and then we attach these whiskers to the drill bit. So as the drill bit is spinning, snow gets flung out and sticks to the bottom of this, but those whiskers then come around and scrape the snow off. So all of the snow now gets directed down to the bottom of the machine. The problem with this initially was we were using foam and stuff, and if you didn't get it aligned perfectly, you would get chunks of foam that would also come flying off and land down on your test surface below. So we had to go back and do some redesigns of that. Then we also had the problem of how do you control the rate of ice being fed into the drill bit to come up with a consistent rate. So we have our tray assembly at the bottom. So we have our 10-degree test surface, just like you saw outdoors. We have a mass balance at the bottom of the machine that's simply weighing the weight of everything on top of it. This is connected up to a computer. So as we run the machine, snow falls down onto the plate. And because we have this nice fluid containment assembly, when we pour the fluid on the plate, any fluid running off the plate gets captured in that fluid assembly, but it's all confined on top of the balance. So we're not losing any weight from fluid coming off of the plate. The only thing that's being added is the snow. So based on the amount of snow that's being added, because of the addition of the weight, we can derive what that snowfall rate is. And so based on that, then the computer can control how quickly it's pushing that ice core into the drill bit. So here is one of our test surfaces. So this gives you an idea of the size of the test surfaces as well as the fluid containment unit. So in any given test, we simply pour the fluid over the top of the plate. We let it run down the plate. And then this would then sit on the mass balance and simply collect the snow as the snow falls down from the top of the machine. So we said, okay, great. We've solved the snowfall rate problem. We know how to do that. Now we've got to design the computer interface. So this became a little bit more challenging. We were able to do it. So we have full control of everything that happens in the machine. We can turn the blades on. We can simply put in the rate that we want the snow. The computer will control that rate. And then we can record all of the information coming out of the machine. So we can monitor the air temperature. We can see the snow mass. So this nice straight line up here shows that we have a constant amount of snow mass being applied to the plate. So we've been able to successfully achieve a constant snowfall rate. So that's the mass, and then we can actually monitor the rates in real time at the bottom of the machine. Great, so put it all together, and here is what the early version of the snow machine looked like. I'm gonna play a little video for you. Initially, we were using a drill press mounted on its side with a bit attached to it to do the actual ice shaving. And you can see from this video that, yeah, you are getting what looks like snow-like particles that are being shaved off of these ice cores and falling down onto our test surface at the bottom. The problem that we were having was that spatial distribution problem. Because we had one point that we were generating snow, we'd get a lot of snow right over the middle of the plate, and then it would kind of taper off as you got out toward the edges of the plate. So we would see this streak of snow that would fall down the middle of the plate, and you would get less out here, which is not realistic for the outdoor conditions. So we said, let's do an upgrade. Let's put 2 ice cores in. And instead of using a drill press, let's swap those out with variable speed motors. We did this. We had some custom design bits for shaving the ice that were designed as well. We were having a lot of problems with the bits getting dull very quickly, also chipping away at the ice, which wasn't giving us consistent shavings that mimic snow. So we had to custom design our drill bits. And we found that the angle of the bit, even by 1/10 of a degree, made a huge difference in the type of snow that you would get out of these ice cores. We replaced the drill press with the variable speed motors. And the advantage to doing that was by controlling the spin rate of the bit, we could actually control the size of the snow particles that we were generating. So slower spin rates means that the ice core isn't being shaved as quickly, you get bigger flakes. Spin it faster, and you're gonna get smaller snowflakes associated with it. So now we can actually control the size of the snowflakes and test these fluids based on particle sizes. So what does that look like? Here's an example where we had the spin rate of the bit really fast. So we were getting these really small particles, these really small shavings of snow. And then when we slowed it down for the same conditions, same rate, same temperature, now we could see that we were getting bigger snowflakes. So this has given us an advantage that we can really look into some of our outdoor environments at warmer temperatures where you may see these big aggregate snowflakes that are falling sometimes, or smaller snowflakes. We can go in and simulate both conditions. We could not do that very easily before. So going back and looking at our requirements that I stated, we have to have size ranges that must be realistic. The density has to be match real snow. The spatial distribution must be even, and fall speeds must be realistic. Up to this point, we achieved 3 of those 4 things, but we were still struggling with the spatial distribution. So we said, all right, we're gonna make one more modification to the machine. So we went back to the drawing board, completely redesigned the system using the same concept. So we're still using 2 different generation points for the ice aloft. But now we've added an additional component. And I'll start this going. Oops. This is the current version of the snow machine as it is now. So you can see the test plate at the bottom, you can see the snow that's falling, but now we have taken the linear translators and put them on linear translators. So those now actually are moving back and forth across the top of the machine so that we're getting this sweeping pattern of snow across the bottom of the machine. And we have found that by doing this, this has essentially finally solved our longstanding problem of an even spatial distribution of snow across the bottom of the machine. So now when we do our testing, instead of getting that line of snow down the middle, we get this nice failure that goes from the top of the plate down toward the bottom of the plate, just like we see in natural outdoor conditions. So we finally checked that last box. And this latest version of the machine actually just came into being last year. So we're literally on the forefront of finally solving this longstanding problem. And I'm gonna talk a little bit about what that means for where we move in the future. Now, I also wanna show you, because I've talked a lot about the fluids, when we apply fluid to the plate, what does it look like in terms of the fluid being absorbed in, or the snow being absorbed into the fluid? Here's an example from the machine itself, where you can see snowflakes coming off, falling into the fluid, and you can see them dissolving into the fluid itself, and the fluid absorbing them and holding on to them, so it isn't adhering to the surface of the test plate itself, and that's what we want to see. So what have we learned on the NCAR side of things? As I mentioned, the fluid is considered failed when 1/3 of the fluid is covered in snow. One thing that we looked at when we first started doing testing was what is happening with the temperature of the plate itself as you're doing these tests. Because the temperature of the plate or the wing is also going to be important. We embedded a temperature probe in the back, and then we ran a simulation. So we had it snow in the fluid. So the figure that you see here, the blue line is the ambient temperature. So the ambient temperature was held pretty close to around -9 degrees Celsius. The green line that you see here is the accumulated snow mass. And again, you want to see a mostly straight line, meaning you've got a fairly constant snowfall rate. And the red line is the temperature of the plate. And the thing that immediately stood out was here's your ambient temperature, but here's the plate temperature. And as the experiment ran along, the plate temperature got colder and colder until a certain point where it bottomed out. And then that temperature started to warm up. And right after that, this line right here is where the visual fluid failure was called, where a third of the plate was failed. So we said, aha, this is what's going on with these fluids. In order for that snow to dissolve into the fluid, it's got to pull heat from somewhere. And it's pulling the heat from the wing or the test surface. So as it pulls the heat out, it cools the surface of the wing or the test surface. So knowing this, we should be able to model this behavior, because if we can model this behavior, then we can have an idea going forward of how long these fluids are going to last under the given conditions. So how do we come up with that? This is the only equation I put in here. I promise it's not that hard to understand. I will walk you through it, I promise. dr dt is equal to r sub s L sub m divided by c rho sub ft. R sub s is the snowfall rate. So we're simply relating the snowfall rate to that temperature decrease. Our snowfall rate, we know, is constant. It's not going to change. We have the latent heat of melting. You can think of that as the heat that's needed to change the snow from a solid to a liquid, or to dissolve the snow into the fluid itself. So the snowfall rate and the latent heat of melting are constants. Those aren't going to change. The things that are going to change is the heat capacity, which is the ratio of the heat absorbed to the resulting temperature change that we see in the fluid or the plate, the fluid density, and the fluid thickness. So if we can model those things, then we should be able to model how these fluids are going to fail. So if we take that and we go back to the example that I just showed you with that plate temperature drop-off, you can see at the beginning of the test, our theoretical cooling matches exactly what the temperature of the plate is doing. And then as the test gets further and further along, because we aren't accounting for change in fluid density or thickness of the fluid, or the change in the heat capacity, our line just remains a straight line going down, while instead the line that we're seeing from that plate temperature dips down and comes back up. So is this something that we can use in the future to help better understand when these fluids are going to fail? Yes, we can certainly use that to give us an idea. Is it something that we can actually use in practice? Probably not. People aren't going to be too comfortable relying just on this model to determine when the fluids are going to fail. We're still going to have to do that testing in a snow machine or an outdoor testing environment. So as I said, the fluid becomes increasingly dilute, which is going to slow the cooling. The fluid thins over time because gravity is pulling the fluid down the plate, but we're also thinning it out because of the water that's being added to the fluid itself. And then the heat will be transferred into the fluid from the ambient room air as well. So it's not pulling heat just from the plate. Primarily, yes, that's where it's coming from. But the air temperature in the room is also impacting that. So how does our laboratory testing compare to an outdoor test? So we were able to take some outdoor data where we put one of these tray assemblies outside. We let it snow outdoors. So you can see the purple line here was the snow mass of the snow that was accumulated outdoors. And then the light blue line was the simulated snow mass that we did in the snow machine itself. And then the red and the blue lines here, the red one is the outdoor temperature of the plate, and the blue line is the temperature of the plate inside of the snow machine itself. So the snow masses match very closely, but you notice that the failure times are different between the two. The reason for this, and if we look over a longer period, we did a whole bunch of tests. It wasn't just this one. This is a good example. But if we do all of them, we see that the testing that we do indoors is consistently shorter than the temperature that we're seeing outdoors. There is some scatter in the data, but it's consistently shorter. The reason for that is wind. Outdoors, you get wind that's blowing over the surface, and your ambient air temperature is warmer than the temperature of the fluid and the temperature of the plate, so you're adding additional heating to the fluid, which is going to make it last longer. So if you want to do the most conservative testing that you can for these fluids, doing it in a laboratory environment like we're doing, where you don't have wind, is actually the best way to go. So where are we at now in terms of next steps? There is an international community that meets that consists of all of the fluid manufacturers, all of the airlines, all of the regulators, meaning FAA, Transport Canada, EASA in Europe, and they get together twice a year. There's a big meeting that's held in May every year, and then a smaller meeting that's held in November, where updates are given on the status of new fluids coming out, tests that are being done on the fluids, and the snow machine is at the forefront of these discussions. Everybody wants to see the snow machine become the international standard for testing these fluids, because you can do it anytime year-round. You can do it in a laboratory environment. You don't have to wait for the right conditions to occur outdoors. You can simulate them yourself. And you minimize a lot of the problems that we see outdoors. You're gonna minimize the scatter that we see in a lot of these different data points. It'll also allow us to assess the impacts of the different snowflake sizes on some of the failure times, because there are questions that we're getting from them where they say, yeah, this one test that we did, the snowflake sizes were a lot bigger than this other test. We think that's potentially a problem. They're also looking to explore the integration of other precipitation types. So now that we can do snow, can we put nozzles in there and also do snow and rain at the same time? And can we come up with holdover times for those types of situations? So this is where we are now headed with this technology. We are hoping at the meeting coming up here in May that once we show the results of what we've been able to do with the machine at this point, that they're going to start moving forward with developing an actual international standard document that will allow for the snow machine to be used for testing these types of fluids going forward. So hopefully within the next year, when we meet in May of 2026, we will have enough testing under our belt that we can go back to the community and say, here's the data. Here's what we're showing. We've been able to reduce the scatter that you see in the outdoor failure times. We understand the impacts of these different snowflake sizes and how they impact holdover times. And here's what we propose in terms of using this machine going forward to establish it as the international standard. So I know I've hit you with a lot of information. I could easily turn all of the information related to ground de-icing into a half-a-day lecture series on everything that happens. I can see that I've bored some of you to tears already. Some of you are falling asleep back there. I won't call any specific people out. However, I do want to thank you for showing up. I want to thank all of the online participants, including the cheaters who showed up to answer some of the questions. I want to thank Mary Poppins for use of her magical podium, for storing my stuff underneath as well. And if anybody has any questions, I will take them from you now.
Alrighty, folks, we're going to switch between in person and online. So if anyone has any questions for Scott in the audience, Perrin will get you the microphone.
As the airplane is accelerating down the runway with all this fluid sliding off the back, what happens when the next airplane tries to land?
Excellent question. That is a question that we have received many times. So the nice thing about this fluid is not only does it act to protect the aircraft wings from precipitation, when it lands on the runway, it can continue to provide some of that on the runway as well. So runway plowing operations, we have another group in our laboratory that has a product that is being used at DIA where they tell them different types of fluids and stuff that they can use to de-ice the runways. This kind of gets grouped in as part of that, where it's used for that. And usually over time, when you get enough snow buildup, it stops providing protection. It will get really slushy, and then runway plowing operations kind of pushes it off to the side. So yeah, it doesn't really have an impact on landing aircraft. Great question, though.
Awesome. Looks like we have some questions that are popping in online, but we'll continue in the audience. Any other questions? We have one right over there.
So why is the test plate reflective? Why not use something that's painted similar to an airplane wing?
Another excellent question. So there are actually standards for the plate. This one, I can tell you right now, is not up to standard. There is a certain polishing level that we have to do on the plate that will very similarly match what you get from an aircraft that's been painted and then had a clear coating applied over that. Yeah. For our purposes, silver is just easiest to use.
Great. I think that actually answered our one online question about that. So we'll still stick with our audience. I think there was a question right over here.
Thank you. Thank you for the lecture today. So I had a question regarding once like the airplane is aircraft. You said that in the sky, the temperatures can actually go down to negative 60 degrees. Do we have to worry about anti-icing up there?
Absolutely. Not so much maybe at the minus 60-degree level, but when you get closer to the surface, you may fly through a cloud where your temperature is -5. And maybe there's drizzle or freezing rain in that cloud, and you're flying through it, which means now you're starting to accrete ice in flight on the aircraft. This lecture is actually part of a mini-series where the next lecture will be given by my colleagues Julie Haggerty and Dan Adrianson on that hazard, where they'll be talking about the problems associated with ice accretion in flight. So yes, it is a problem. Yes, there are aircraft accidents that happen every year because of that. There was recently one just outside of Nome that is suspected to have been caused by that condition. But Julie and Dan will have another great lecture series talking about what causes that and what we at NCAR have been doing to help mitigate that.
Awesome. Thanks for that question. We're still stick with the audience right over here.
Thanks. So I get that the spin rate affects the average size. And you can probably also tune it to the total snowfall rate. But I guess the process in the actual atmosphere, lots of things are going on, make bigger and smaller things. So I'm wondering about the size distribution. How do you get the size distribution to be the same in this laboratory where you haven't had that evolution?
Excellent question. Interestingly, one thing that we have noticed with the machine, we can take the machine and we can set it to do a rate of 0.1 inches per hour. And we can set it to do that at a temperature of, let's say, 28 degrees Fahrenheit. And we can look at the snow coming off of that. We can set it at a constant spin rate, we'll say a spin rate of 3. And then we can do that same exact test, and we can do it at a temperature of 5 degrees Fahrenheit. Not changing anything except the temperature, and we will actually get 2 very different size distributions. The warmer temperatures, we naturally get the bigger flakes. They'll be a little bit wetter. They tend to more closely resemble the natural size distributions that we get outdoors. At the colder temperatures, we get the much smaller flakes, but again, it tends to naturally mimic some of the natural variability that we see in the size distributions outdoors. So it's almost a serendipitous side effect of the machine that it's naturally creating these size distributions that we would see in nature. Yeah, another great question.
Awesome. I'm just going to plug it in for my online folks, even if you're the cheaters, to please ask some questions for Scott. We'll still continue in the audience here. I think the gentleman right over here had his hand up.
I know in a de-icing area, they have drains that this excess fluid drains into, so it's not going into the rivers and that. Is there a similar things along the runway that collects all the runoff from the runway?
Great question. That I don't think there is so much because it kind of gets mixed in with the natural runway de-icing fluids. It tends to just kind of, once the snow absorbs it, they push it off to the side, and then over time, it kind of breaks down naturally on its own. It's a reason that they use the propylene glycol fluids because they are considered an environmentally friendly fluid. Propylene glycol, aside from being used in cars, is used in literally everything. If you look at soap, shampoo, all sorts of everyday products and stuff, more often than not, even some foods, you will see actually have propylene glycol in them. So it's less of an environmental concern in that regard because it will kind of naturally break down. It may take a little while, but it does break down.
Awesome. And we'll go right here in the front.
Probably a silly question, but why can't you heat up the wings to melt it?
Great question. In flight, you can. And on the big aircraft, I'm stealing a little bit of Julie and Dan's thunder here. But the bigger aircraft, when you're in flight, oftentimes what they do is they vent the exhaust from the engines kind of through the wing surfaces themselves, which tends to keep the wing surfaces really warm so they don't accrete the ice. The problem on the ground is the engine's not running. So you don't have that exhaust on the surface of the wings on the ground, so you have to apply these fluids until the aircraft can become airborne. There are other de-icing methods they've looked at. There's experimental techniques out there where you can take infrared lamps and go over the surface of the wing to try to melt everything and get it really warm to the point where you can try to quickly take off and become airborne to let the onboard systems take over before the wing starts freezing up again. It's been very hit and miss on some of those technologies, but also adding things to the wing in terms of trying to put internal heaters in the wings to keep them warm on the ground adds weight, it adds complication and stuff to the wings. It would only work at airports that you can actually plug into power. So some of the smaller airports, that may not necessarily be an option. So for now, this is what we're using. Yeah, good question.
We have a question back there.
Thanks for speaking today. My question is a little bit more related to the meeting that you said comes up in May. So when we have like all these stakeholders coming together, you said the FAA, airlines, plane manufacturers, who's, I guess, the ultimate decision maker who might, make this a standard, where I would say the FAA might be more concerned about safety, but then airlines might be more held responsible for failures of products like these?
That is an excellent question. And this specific meeting is held specifically to establish standards. So they have buy-in from all of the stakeholders. All of the data is presented to them, and the stakeholders will come forward saying, all right, we've reviewed the data. We feel that this is a viable method for going forward. So now we want to pursue establishment of developing what that standard is going to be for using a technology like this. And generally, when the standards group comes together with all of them and they're saying, yes, we all approve this, then you sit down and you write the standard. That's a whole other process because you literally have to make sure you address everything. How is the fluid going to be poured on the plate? How are you going to operate the machine? How are you going to do the fluid failure calls? Literally everything that you can think of goes into writing the standard. And it can take 1, 2, 3 years just to get the standard to the point where everybody is happy. So getting everybody to agree on it is one thing. Then you have to write the standard and go back to them at every meeting and say, here's the progress we've made on the standard. This is the language that we've put in there. Is everybody happy with this? And there can get to be some very spirited discussions at some of these meetings over some seemingly innocuous wording on how some of this is done, but they want it to be very specific so that there is no ambiguity, so somebody reading this can understand very clearly, these are the steps that you must take to do this. So yeah, it's definitely everybody coming together saying, yes, we want this.
Question in the back.
Thanks, Scott. On this, it's also the standard for the equipment that's making the snow too, right?
Yes.
Standardizing how that's going to be built, how it will be operated on top of the
Correct.
processes.
Yep. So we will establish things over like temperature ranges. The equipment must operate over a temperature range of 34 degrees Fahrenheit to 0 degrees Fahrenheit. We actually, a lot of the testing we can do, we can easily run this machine down to minus 25 degrees Fahrenheit without any problems. We haven't tried going colder than that because our cold laboratory doesn't go colder than that. But we haven't seen any indication that it couldn't go colder than that. So if somebody has a facility that can go colder, we can probably accommodate that. But things like that, temperature ranges, it must simulate snow over a range of 0.015 inches per hour up to 0.25 inches per hour. Things like that will get put into the standard so that if somebody wants to come along and try creating a new machine to meet the standard, these are the specifications that you have to meet before your machine will also be accepted.
Excellent. Question down here.
Hi, thanks, Scott. So it obviously took you guys a little while to get this machine operating in a way that was favorable to the tests that you guys had to do. I was curious about what kind of major stumbles or shortfalls you might have had in creating this, like other than your snow guard, because I know making that kind of machinery can be a little finicky sometimes. So I was just curious.
Very much so. Certainly the transition from the drill press to the variable speed motors was another huge step in that technology. The drill press would work well at warmer temperatures, but at really cold temperatures, the belt gets stiff and then it doesn't want to turn. So you would have to go in there literally with a hairdryer and warm up the belt first and then turn the machine on to get it to work. In some cases, it's been incremental steps that we have applied to solve a specific problem. Part of the reason that it took 20-some years to get to the point of where we are was interest in the snow machine kind of waxed and waned over time. There'd be a lot of interest, and so we'd get a lot of money, and then we'd make some progress, but we were still having problems, and then the FAA would kind of become disinterested. But this committee that meets every 6 months kept coming back saying, we need this. We need to figure out how to make this work. And so finally, in 2018, I went to the FAA and I said, all right, look, if you want to solve all the remaining problems with this machine, I need some money. And I don't need a little bit of money. I need you to really invest in this machine to make sure that this technology is going to be viable. And so the FAA said, okay, we're going to step up to the plate. And they did. So we got a significant amount of funding. And over the past 2 to 3 years, we have seen significant improvement in the technology and the ability to create snow, even distribution, get failures that look exactly like we do in the outdoor environment.
As a follow-up to that, I was curious of the additional funding you got. Does it go towards better components for the machine or just more people on the team working on it?
It mostly went to upgraded components of the machine. So the team working on this is not a big team. I'm the lead scientist on this. I have an associate scientist, Justin Lentz, and I will credit Justin because he really is kind of the brains behind the development of this. He's a mathematician by training, but he has very much an engineering mindset. So when we brought him on the project in 2016, 2017, he looked at this and he said, we can do better. And here are some ideas. So we started pitching that to the FAA and got them excited, and that helped in terms of getting the additional funding in. We also have a software engineer, Andy Gatos, who deals with the entire interface behind the scenes of getting the computer components to work. The snowfall rate component of that, while it may seem simple, you simply just push the ice core in at a constant rate, took years also to get adjusted because you can see from the ice cores, if I pull this up, there's air bubbles and stuff in there. So if you're pushing it in at a constant rate, you're gonna hit some of those air pockets and stuff that are in there. So you're not actually gonna get a consistent rate all of the time. It'll go up, it'll go down, it's gonna kind of vary. So our software engineer was able to come up with an algorithm that was monitoring this in real time, and if the rate was going too high, it would slow it down in terms of feeding the ice core in, and if it was getting too low, it would speed it up. So that throughout the duration of the test, if I want 0.01 inches per hour average rate, by the time I got to the end of the test, I had 0.01 inches per hour.
Oh, thanks for the talk.
Thank you.
Got a question right there next.
I just have a quick question about the failure time of this liquid. And you said if a third of the plate is covered in snow, it's considered failed. But isn't this a little subjective? Depending on the person, it might be still a quarter or a third. Is there a very specific quantitative way to define this failure time?
Thank you for that excellent question. The answer is yes, it is extremely subjective on how these fluid failures are called. That was another reason that we were looking at the plate temperature. Can we use the temperature profile of the plate to determine when the fluid is actually failed? And that is another component that we're actually now trying to push as part of the snow machine technology, saying, look, you can, in real time, be monitoring the rate of the temperature decrease on the plate. And when you see it gets to the point where it's leveling off and it's not cooling anymore, you know you're very close to failure. So being able to standardize on that is another thing that we're hoping to be able to do moving forward in the future. Because yes, I can take 2 independent people, I can send them out into the field, and I can say, tell me when that plate is covered by 1/3 of the snow. And I will get 2 different answers. In fact, we've done it in the past where there have been 4 or 5 of us out at the site. And one night I said, all right, I don't want anybody to say anything to anybody else. I simply want you to go out there and watch and write down the time that you think that there was 1/3 of the plate that has snow covering it. Every single one of us had a different time at the end of that. So yes, trying to get away from the subjectivity of that 1/3 is another reason that we're moving in this direction.
Great. We have a question right in the front here.
Oh, hi, and thank you very much. Great fun and interesting talk that you've given. You just stole my question, so I'm going to have another one. This is slightly left field. I've just come up from Boulder to this talk from the Arctic Science Summit Week. Some people are interested in snow for quite a different reason. It's disappearing, and making snow is one of the geoengineering kind of projects that's going on. So I wondered whether maybe already you're thinking about other applications for what you're doing.
Also an excellent question. Yes, in fact, we've been using it for slightly other applications in the development process for anti-icing fluids. We have used it to test new precipitation gauge technologies. That's one area that we've seen use. We also have use from the drone industry. Drones, as most of you know, is kind of an exploding industry right now. Everybody wants to get a drone, everyone wants to fly a drone. The future is flying cars. We're gonna move from building top to building top in big cities and not have to deal with congestions on the roads. And everybody's kind of like, yeah, this is where we wanna move, but nobody's really thinking of the weather component of that yet. So some of the drone manufacturers now are thinking, okay, if we wanna fly in those conditions, we have to be able to fly in snow and rain and some of these different types of things. So we have been working with one of the universities at Oklahoma State University, some of the scientists there who have developed their own drone with instruments and stuff, who are interested in putting it in this type of an environment to say, hey, when my drone takes off, how long is it gonna last before the drone ices up and falls out of the sky? So we've used it for that. We've also done pavement testing with this. So we've taken different pavement samples, concrete, asphalt, put them in the machine, run them at different rates and different temperatures, and used some of the new pavement sensor technology that's out there to try to make a determination visually of when we see that snow is building up versus what the sensor is saying. So there is a lot of different applications that this technology has that we're just starting to explore now that we have it to the point where we're happy with the technology.
Question in the back.
This was relating to, I don't know your name, but the person right in front of me, hello. Kind of going back to the ice cores and themselves, have you thought about getting like what happens if you end up using clearer ice and like trying to standardize the way you are making the ice cores? And does it matter that much if there is like, of course, to like snowfall rates and such, but outside of just that, is it matter that much, or is that you can fix it with an algorithm?
We pretty much fixed it with the algorithm. We had explored different techniques for making clearer ice to try to get the air out of it. You can boil the water for long periods, and that helps get rid of some of the dissolved air. That obviously takes time. But in the end, we simply said we can come up with an algorithm that will on the fly adjust for that sort of thing. Also, when we're doing a legitimate testing of the fluid, you can't use tap water because there is the potential for some of the chemicals that may be dissolved, natural chemicals dissolved in tap water that could have an impact on the failure times of the fluids. So when we create the ice cores, we actually use distilled water and freeze them and then use more of a non-contaminated water source for the ice.
Awesome. We got one last question here in the audience, and then
Thanks, Scott. Kind of going off of Annika's question, I get in the testing environment having like a really, control of all the variables, but like on actual planes, there's a lot more particles and stuff that is in the snow. So when you want to, I guess, like try to, I don't know, do that in the lab as well at times, or?
I think that's potentially part of some of the future plans, especially looking at possibly scaling up this technology. So we can very easily cover a surface with this area, but the drone industry has come to us and said, can you build this up? Can you make it bigger? Instead of using 2, can you do 12? Can you do 20? Can you really distribute the snow over a much broader area so that we can test bigger things? So I would say, along with that and looking at multiple precipitation types together, we'll probably at some point end up addressing that.
Sure, go for it.
I was just curious about the de-icing and like rotor wing, like helicopters, and the kind of differences that type of aircraft faces when using de-icing. I assume they do, but I imagine it's applied differently and has different kind of practicality in different environments.
Helo is a very different beast, for sure. You have to be very careful which fluids you get or which surfaces you get the fluids on a helicopter. The same is true of aircraft. There are certain surfaces on the aircraft you simply have to avoid when you're applying de-icing fluids, because these fluids get everywhere. An aircraft will take off, it lands at another airport. It could be landing in Miami in warm temperatures. The landing gear comes down, and when the ground group goes out to pull the baggage off, there's fluid dripping out of the wheel well compartments and stuff. So helicopters, you have to really just stick with the blades, and that's it. Try not to get it anywhere else. Yeah, very different.
Awesome. Well, if folks have more questions, Scott will stick around for a little bit after the presentation, but why don't we go ahead and give him a round of applause for a great event.
Thank you, everyone. And thank you, NCAR, as well, the EDC group, for hosting me. I hope you all learned something, enjoyed the talk, and I'm happy to hang around and answer some questions.
Awesome. And I have a short blurb, and then I'll let you go, I promise here. So thank you all again for attending this incredible lecture on de-icing as part of our Explorer series. We hope to see you again online on April 16th from 5:30 p.m. Mountain Time for our next event, where we will chat with Daniel Adrianson and Julie Haggerty on the hands-on aircraft icing experience and icing forecast products that keep us safe in the skies. If you're interested in more NCAR Explorer Series events, check out our website for upcoming lectures and conversations and view recordings for past events. Please, 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 if you are over 18 years old, please take a moment and fill out our 3 to 5 minute anonymous survey to help us better understand the impact of this program and how we can improve the next event. The survey will close on Monday, March 31st, so you have a bit of time. You can find the survey by scanning the QR code there and there. You can also ask a staff member if you would like to take the survey using one of our tablets. And again, I hope to see you all next time and have a great rest of your evening. Thank you.